Let's continue with chapter 13 and discussing equilibrium. As we had seen in previous lectures dealing with translational motion, we defined equilibrium to occur when the sum of all the forces acting on the body is equal to zero. That meant that acceleration is equal to zero. Well, a body could be in rotation where its center of mass remains that doesn't translate through space but nevertheless it's rotating. So for complete equilibrium, then we also need to make sure that the net torque, or sum of all the torques acting on the body, is equal to zero, which implies that the angular acceleration of the body is zero. So this here, net force equaling zero and net torque equaling zero, is complete equilibrium for an object. So a rotating body which is rotating at a constant angular velocity omega is also in equilibrium, rotational equilibrium. And as you already know, if a body is moving with a constant velocity, of course that body is in equilibrium as well. So the conditions that one needs to satisfy to show that an object is in equilibrium is summarized here. Net force acting on the body is equal to zero, and net torque acting on the body is equal to zero. So let's start with a very simple example, one of a beam, a uniform beam of mass m. So if the object is said to have uniform mass m, a uniform mass distribution, or its length L, that means that force due to gravity acts at the midpoint of the object. Remember, the center of mass for a symmetric object is at the center. So this distance here is L over 2. So now if this beam is supported at either end by support 1 and support 2, now let us figure out the normal force on N1 and N2. So here we have, let's identify our forces. This is normal force due to due to support 1, normal force on the beam due to object 2, and of course we have force due to gravity mg, which is acting at the center. Now the object is in equilibrium, it's neither translating nor rotating. Therefore, we know that the sum of all the forces acting on the body is equal to 0. Sum of all the forces are N1 plus N2 minus mg. Once again, here I've chosen the up direction as my positive direction. That's equal to 0, which means that N1 plus N2 is equal to mg. Now we have two unknowns here, N1 and N2, and only one equation, so technically we cannot solve it. Intuitively, of course, you know that N1 must equal N2, but as I say, there are circumstances where you cannot make that assumption. So a second set of equations can now be obtained. So this is our first equation. Second equation can be obtained by considering the rotational equilibrium. So sum of all the torques on the body must equal to 0. Now to figure out torque, one thing that you need to do is choose your pivot point or rotation axis. So if we were to choose, we mark it with red, where support 1 is as our rotation axis or pivot point. So this is torque about 1, Alright, about 0.1. Now, if you have unknown forces, it behooves you to choose your pivot point at one of those, at the position where that unknown force acts on the body, because then you know that the torque due to that unknown force is going to be equal 0. So you eliminate one of the terms in your equation. So what is the net torque then about position 1? Well, we have, let me write everything out. So we have N1 multiplied by 0. 0 is the moment of arm to support 1. And so that's just 0. Then we have force mg times L over 2 is our moment of arm. And mg acting on the beam alone would cause a clockwise rotation. Therefore, would cause a clockwise rotation, therefore it is a negative torque, right? And then we have N2, so we have N2, and the moment of arm is the whole length of the beam, which is L, and N2 acting on the beam would cause a counterclockwise rotation, therefore it's a positive torque that must equal 0, which means that N2 is equal to, if you simplified, mg divided by 2. So that's your second equation. So plugging N2 equals mg over 2 into your first equation, by combining these two, you end up with N1 is also equal to mg over 2. Just a simple example to show how one goes about using equilibrium argument to figure out forces acting on a body in equilibrium. Now let's entertain a slightly more interesting scenario. In this case, let's say we have our beam. Once again, uniform mass distribution, so you know the force due to gravity acts at the center. So let's say that the beam has mass m, right? So here is our force due to gravity acting on the beam, and once again this is L over 2 if the length of the beam is L. Right? And in this case it is supported by support 1, position at one end, and support 2, which is positioned somewhere a certain distance away from the right end of the beam, so distance x away, right? And let us also position some mass. So here I put a box. Let's call this mass big M, which is distance little l away from the right hand side. Now, what are the forces acting on the beam? Well, we identified mg, force due to gravity, acting on the beam. Now, in addition, we have normal force here on support 1, normal force due to support 2. There is also the mass m sitting on the beam. Now, for simplicity's sake, we can show the force due to the mass m being positioned on the beam as mg. Now, technically speaking, let me draw blown up version of that right hand side. Technically speaking, we have big mass m sitting on the block. The forces on the block are the normal force from the mass onto the block. Now, this normal force is an action-reaction pair with the normal force from the beam on the block, and that normal force on the block has the same magnitude as the the weight of the block. So when we show the force acting on the beam as mg, what we are implying here is that the magnitude of the force due to the block being positioned on the beam is equal to mg. Technically speaking, it's the normal force from the block that is acting on the beam, not the weight of the beam acting on the beam, of course. But for, as I say, to keep things simple, it's by writing mg, you've identified the force the right direction, and mg is its magnitude, of course. So I just wanted to clarify that briefly. Now, once again, to solve for equilibrium, I guess you can argue that the sum of all the forces is equal to 0. What are sum of all the forces? We have n1 upwards minus mg plus n2 minus big mg. Alright, so that whole thing must equal 0. Now sum of all the torques must also equal to 0. Once again, n1 and n2, let's say, are unknowns. Once choose your pivot point to coincide to the position where one of the forces, unknown forces, is applied. So let's make that position 1. n1 times 0, that's 0 torque. Then we have minus mg times L over 2. Now torque due to m2 is, we have force n2, and what is our moment of arm? Moment of arm is from position 1 all the way to where the force is applied, which is L minus x, and it is a positive torque because it would cause a counterclockwise rotation. And finally we have mg, and its position is L minus little l, and it's negative torque. So all this jazz must equal to 0. So if you can solve for the unknown using these two equations, fine. However, if you have yet another unknown, you can come up with a second pivot point. Now let's choose our pivot point to be here. So now let's do the torque due to support, about support 2. Now we know that that's equal to 0 as well. You can pick the pivot point to be anywhere, so long as you know the object is in rotational equilibrium. Where you choose the pivot point is arbitrary, because you know that the sum of all the torques calculated about that pivot point must equal to 0. So about this pivot point, what do we have? Let's start with the left hand, the very far left hand side. We have n1, and the moment of arm is L minus x, and n1 acting on its own on the beam about position 2 would cause a clockwise rotation, so it's a negative torque. Next force is mg, and this distance is, what is that distance? L over 2 minus x, L over 2 minus x, and acting on its own counterclockwise, so that's a positive torque. Then we have n2, and that's a 0 torque, 0 moment of arm. And then finally we have mg, which is positioned x minus little l away, and it would cause a clockwise, so it's a negative torque. So all this jazz must also equal to 0. So you see that you can go ahead and set up as many simultaneous equations as you have unknowns to solve for all the unknowns. So here I have three simultaneous equations, and excuse me, have three simultaneous equations, and had I three unknowns like n1, n2, and x, for example, then I could solve for all three. If I need to go about and set up yet another equation, then I can, for example, go ahead and choose the center of gravity of the beam as so the pivot arm. So the torque about center of gravity, what is that? That is, let me go ahead and write that, minus n1 times L over 2 plus mg into 0, and then we have plus n2 into L over 2 minus x, and then we have mg negative into L over 2 minus L. That must equal 0. So now I have four simultaneous equations. The rest of the exercise is an algebraic one, so I'll leave that to your pleasures to go ahead and practice with.